This is a diagram and the formula of the thermal analysis. It may look very complicated, but the concept behind it is actually very straightforward. Thermal calculations are poorly understood, and the most common problem is not the maths going wrong. The maths is fine. The problem is running a generic calculation that does not match how the wall was actually built. The numbers checks out. The wall does not. In this video, we will cut through that. We will look at what thermal analysis is actually measuring, how to pick the right calculation method for your construction, what to do when your results does not pass, and the gap between the report and the site that no calculator can see. My name is Eugene Korch. I teach and practice facade engineering, and today we are talking about thermal analysis of external walls. Before we get to any formulas, there are two parameters you need to know. The first is total thermal resistance, the R value. Think of it as the armor of your wall. The higher the number, the thicker the armor, the harder it is for the heat to get through. In North America, external walls are regulated using R value. The second is thermal transmittance, the U value. Think of it as the leak. It measures exactly how much heat drips through every square meter of the wall every second, all winter long. The lower the number, the smaller the leak. In Europe and the rest of the world, external walls are regulated using U value. They describe the same wall from opposite directions. As R value goes up, U value comes down. Their product always equals 1. U value multiplied by R value equals 1. So before you calculate anything, know which number your jurisdiction requires and what your target is. North America, R value. Europe and most of the rest of the world, U value, measured in watts per square meter Kelvin. A modern rain screen facade wall has 6 or 7 layers. None of them are there by accident. Let us use a standard rain screen, the kind you will find anywhere from southern Spain to Glasgow to New York. It starts at the room, internal finish, usually a double layer of gypsum board, then a vapor control layer, then the structural layer, a steel frame with mineral wool between the studs, or solid masonry. Each one of these materials is uniform through its thickness, with one exception. The stud wall is not a single material. It is composite, steel studs and mineral wool infill side by side. Outside there is a structure, a sheeting board, then a water barrier membrane, also known as breather membrane, then the insulation layer, then an air cavity, and finally the outer cladding. Not every layer gets counted in the calculation. Vapor control layer and the breather membranes are skipped. They are simply too thin to make any meaningful impact on the result. Now, the air cavity. It comes in 3 types: unventilated, slightly ventilated, and well ventilated. The classification matters. Each type is treated differently in the calculation, and getting it wrong will shift your R value and U value, sometimes enough to change the outcome. A well ventilated cavity means fresh air is constantly flushing through. The air stops insulating, and the moment that happens, the thermal boundary shifts inwards to the outer face of the insulation. Everything beyond that line disappears from the calculation. The air gap, the outer cladding, regardless of what it is made of. A brick slip rain screen in this situation and the aluminium panel contributes exactly the same to R value, 0. This is why cavity classification matters. Confirm the type before you open any calculator. There are 4 levels of calculation. None is more correct than other. Each has a place and each has a scope. The question is not which one is best, it is which one fits the construction in front of you. Pick the wrong level for the job and the calculator will not warn you. It will just give you the number that does not reflect your wall. So, level 1, manual calculation. Take each layer's thickness, divide by its thermal conductivity, and you will get the R value contribution of that layer. Add every layer together, plus the surface resistance at both sides. That total is your R value. Divide 1 by R value and you will have your U value. Fast, transparent, and indispensable for building intuition. But it only works where every layer is one uniform material all the way through its thickness. And we just saw stud walls and rain screen substructures are not uniform. Level 2 as a simple online calculator, useful for early stage estimates on straightforward construction. Same scope as manual, homogeneous layers only. And it has the same problem. In a simple calculator, there is no way to enter steel studs or cladding brackets. The entire lightweight steel frame layer gets entered as a primary material, insulation. The steel simply does not exist in the model. The result will overestimate R value by 20 to 30%. Level 3, an advanced online calculator. This is the tool for any wall with steel framing. rain screen brackets, or mixed material layers. It carries a bracket correction database built from real three-dimensional thermal simulations. The result after correction gives you the R value and the U value reliable enough for preliminary assessment and regulatory submissions. Finally, level 4, finite element analysis. This is the desktop calculation that builds the correction database the level 3 tool relies on. The idea is straightforward. You take the entire wall, every stud, every bracket, every layer, and divide it into the fine grid of tiny cells and interfaces. Then the software solves the heat flow through each cell or the interface in 3 dimensions and pieces them all together. The output is complete thermal map of the wall, heat finding its way through the brackets, through screws, along slab edges. It's the most accurate calculation available. It is also the slowest, and it needs specialist software. You reach for it when the project demands certainty. That's complex geometries, unusual assemblies, or when the calculation has to be defended. So what if the result does not pass? The U value comes out too high or the R value too low for what the code requires. The wall is not insulating enough. What now? Well, you have 3 levers at your disposal. They are not interchangeable and the order matters. Lever 1. Insulation thickness. At early design stage, this is the simplest move available. You are not yet locked into specification. Nothing has been priced. Nothing has been approved. You just lay in more depth from the start and the R value responds immediately. Once the project is further along, even this lever becomes complicated. So use it early while it's still free. My personal advice is overshoot. Add 20% more insulation than the calculation says you need. That buffer will be eaten away later by the thermal bridges you have not found yet, the brackets you did not know were there, or the slab edges you missed. Trust me on this one. Lever 2, the insulant itself. If thickness is already fixed, planning constraints or tight facade zones, switch to a higher performing material, for example, PIR insulation or polycyanurate insulation, and I hope I pronounced that right. PIR insulation at the same thickness delivers significantly more R value than mineral wool. But before you make that substitution, check the fire classification requirements for your building. PIR has limited combustibility, meaning that it's still combustible. And every layer in the external wall carries a classification, not just the insulation. One non-compliant material can compromise the entire system. Lever 3, thermal bridges. Every metal bracket bolted through the insulation is an express lane for heat. It bypasses the insulation entirely and pulls the R value down. There are 4 ways to address it. Add thermal brakes pads under the brackets, or increase the stud spacing so there is less steel per square meter. Switch from steel studs to timber. A timber stud still conducts more heat than mineral wool, but the gap is around 400 times smaller than with steel. And change the bracket material itself. Stainless steel is significantly less conductive than aluminium. Stainless steel costs more, but it's still often the cleanest way to recover the R value you have lost. But please check fire classification requirements before specifying timber studs instead of lightweight steel frame. This is only a 10-minute video and we have barely scratched the surface. If you want the full picture, worked calculations for every construction type, cavity specification in detail, and compliance documentation walkthrough, we run a detailed technical webinar at IST. The link is in the description. Here's the uncomfortable truth about any thermal calculation. It describes the wall in perfect condition, not the wall you will actually build. The built wall is always worse. There are 3 things that consistently push real performance below the calculated value, and none of them are unusual. They happen on almost every project. First, installation gaps. A void at the board edge. Insulation not cut tight around penetrations. Each one bypasses the insulation entirely. The heat finds the gap and goes straight through. Once the wall is closed, you cannot fix this. It must be right during the installation. Second, moisture. Wet insulation conducts heat more readily than is declared dry value. If wet materials are sealed into the walls before they dry out, that performance loss is permanent. The thermal conductivity rises above the declared figure and stays there. Protecting materials on site is not a formality, it is part of delivering the R value you calculated. Third, junctions. Your calculation models the middle of the wall, clean, flat, uninterrupted. But real buildings are full of edges and interfaces. The wall meets the roof. Windows cut through the construction. At every junction, heat escapes in multiple directions simultaneously, not through one flat plane, but around corners, along slab edges, through reveals. The plane calculation misses all of it. These losses are quantified separately as psi values, 1 per junction type. A calculation without psi values tells you how the wall performs between the junctions. It does not tell you what the building actually loses. Let me leave you with one scenario, the kind that keeps coming up. A calculation signed off, a building handed over, and 2 years later, energy bills 40% higher than predicted. How does that happen? Usually, one of 3 ways. The wrong tool was used. The steel studs were invisible to the calculator, so the R value looked better than in reality. Or the calculation was right, but the installation was not. Gaps, wet materials, missed junctions, or both. The results of the report is not a guarantee. It's a ceiling, designed with R value above the minimum and U value below the maximum. Not because the code demands it, because the site demands it. Same chain every time. Cavity classification first, right tool for the construction type, safety margin built in, documented so it can be independently checked. That is what turns the number into the wall you can actually trust. And if you want to go deeper, full calculations, advanced tools, and the complete documentation process, the course link is below, and I'll see you there.